In this video, we are to find the average rate of change of the function f of x equals arcsine of x over the given interval, and we are to give that average rate of change in exact form. First, I'd like to remind you that arcsine of x is just another way of writing inverse sine of x. And if you're using a TI calculator, this is the notation you would see instead of arcsine. As a quick review of some facts about sine of x and arcsine of x, I've graphed the sine x function from negative 2 pi to 2 pi on the x-axis, and recall that over that domain, the sine function is not 1 to 1, which is an issue because we want to find an inverse function. And if sine x is not 1 to 1, there will be no inverse function, and it's very clear that we are saying that the inverse sine is a function because we're using function notation. So what's done here is we restrict the sine function over a more limited domain, in fact from here to there, and we only consider this part of the function for x values between negative pi over 2 to pi over 2. So that's what you should see down here. Here's a graph of the sine function over that more limited domain. Notice the x min is negative pi over 2, and your x max is positive pi over 2. And I'm still keeping the y min and the y max negative 1 and 1. Notice over this restricted domain of the sine function, the function is 1 to 1. Every y value will have only one x value, meaning that when we invert it, every x value on arcsine will have only y value, making it a function. Also remember that when you go from a function to an inverse function, the domain of one function becomes the range of the other, and the range of your original function will become the domain of its inverse. So notice that although we restricted the domain of the sine function between negative pi over 2 and pi over 2, that becomes the range of the inverse sine. So notice for the function arcsine of x, I have my window, my y min and y max, going from negative pi over 2 to pi over 2. Again, because the domain of sine becomes the range of inverse sine. Also notice that the range of the sine function was negative 1 to 1, and on the arcsine, I have a window that has a domain of negative 1 to 1. So the range of sine x corresponds to the domain of inverse sine x. Having said that, let's make sense of the question being asked. We're trying to find the average rate of change, or the slope of the secant line, connecting the 2 points whose x values are given in this interval. So recall that in an interval, this is your first x value and this is your second x value. So as points, you'd have negative square root of 2 over 2 as your first x value, and then as a second point, your x value would be square root of 2 over 2. We need to evaluate the arcsine function for those two x values to find the corresponding y values so that we can find the slope of the secant line passing through those 2 points. To give you an idea what this looks like visually, I'm going to type second sine x and graph the inverse sine function from negative 1 to 1 and y values from negative pi over 2 to pi over 2, and I'm trying to get a sense of where exactly these points lie on the graph. So as an estimate, I'm going to press trace. I will type in that first x value of negative square root 2 divided by 2, press enter, and you'll see that when x is roughly negative 0.7, the y value is roughly negative 0.8. This gives me a rough idea of where that point would be. So this information could not be used to find the exact answer, but it gives me an idea where to plot things. If this is negative 1 and my point has an x value that's about negative 0.7 and a y value of about negative 0.8, that point is somewhere right here. Now I can type in the other x value of positive square root 2 divided by 2, press enter, and see that when x is square root of 2 over 2, or roughly 0.7, the y value is positive, roughly 0.8. So square root of 2 over 2 is roughly 0.7, and the y value came out to be roughly positive 0.8. So on the graph, that comes out to be somewhere around here. When we find the average rate of change, what we're doing is finding the slope of the secant line that passes through those 2 points. So the red line that I've drawn here would be that secant line passing through the 2 points on the curve, and our job is to find the slope of that secant line. So if it weren't for the directions saying we have to find an exact value, we could get an estimate just by finding the slope between these 2 points. But since we're asked to find an exact value, we need to evaluate the arcsine function for these x values. So first, we must plug in negative radical 2 over 2 into the arcsine function, or I'll call that inverse sine. And I'm going to use the unit circle to evaluate that. So remember that with an inverse function, the input is a ratio of sides. In fact, that ratio would be the opposite over the hypotenuse. And the output of this function would be some angle. Quickly to remember the rules of applying an inverse trig function, in this case inverse sine of a negative number, we have to remember which quadrant the answer needs to be in and what orientation, positive or negative. One way is to simply look at the graph and notice that if your ratio is a negative number, which it is, it's negative radical 2 over 2, that your output, which was an angle, would be this y value at this point, which is most decidedly negative, right? My x value is negative and my y value is negative on this point right here. So the ratio is negative and we're looking for a negative angle. So you must report your angle in a negative fashion. Another way to remember this, I have this little cheat sheet that tells myself what quadrant I'm looking for as an answer for the angle and what orientation. Since we're plugging in a negative number, specifically negative radical 2 over 2, into the inverse sine function, we're looking at this part right here. This says if you have a negative input into the inverse sine function, the answer is in quadrant 4. I know that because I wrote this information in quadrant 4. And also notice the arrow in quadrant 4 has a negative orientation. It's going clockwise. So that being said, let's look at the unit circle. And since on the unit circle the sine function appears as the second coordinate of the point, I'm looking for where on the unit circle I have a point whose second coordinate, or y value, would be negative radical 2 over 2. If that makes no sense, remember that this question, inverse sine of negative radical 2 over 2 equals question mark, could be rewritten as the sine of some angle, question mark, comes out to be negative radical 2 over 2. So we're looking for the angle whose sine would come out negative radical 2 over 2. Scanning the unit circle, I see that this point right here has a y value of negative radical 2 over 2, and this point over here has a y value of negative radical 2 over 2. But remember, we're looking for an answer in the fourth quadrant, and we have to represent that angle in a negative orientation. So I'm going to be using the answer in quadrant 4, which would be this angle right here. So we need to take the angle 315 degrees, or 7 pi over 4, and we need to represent that angle in a negative orientation. And a quick way to do that is just to notice, to get to that spoke on the unit circle, whose second coordinate is negative radical 2 over 2, you would have to rotate clockwise 2 spokes. So what would it be if we rotated counterclockwise 2 spokes? That would be 45 degrees, or pi over 4. So since rotating counterclockwise 2 spokes is pi over 4 radians, then rotating 2 spokes clockwise would be negative pi over 4 radians. So I have my answer here. The output was negative pi over 4. You can think of it as that is the angle that gives you a sine of negative radical 2 over 2. Now I just repeat with the second point. In the second point, we're plugging positive radical 2 over 2 into the arcsine function. So I'm going to delete the negative symbol. And the question is very similar, except for now we're looking for the angle so that the sine comes out to be positive radical 2 over 2. So we'll be looking for a point on the unit circle whose y-coordinate comes out radical 2 over 2. There should be 2 of them. Here is a point on the unit circle whose y value is radical 2 over 2. And here's a point on the unit circle whose y value is radical 2 over 2. So am I supposed to use the angle in quadrant 1 or 2, and should it be a positive or negative orientation? One way to look at it is you're plugging in a positive ratio of radical 2 over 2, and notice that the output is a positive angle. Or if you like my cheat sheet that I call it, since we changed to the second point, we are now plugging in a positive number into the inverse sine function. And if you look where I wrote that would be in quadrant 1. We're plugging a positive number, in this case radical 2 over 2, into the inverse sine function, and this is written in quadrant 1, so I know I'm looking for a quadrant 1 angle, and notice that the angle I drew in quadrant 1 has a positive orientation. It is going counterclockwise. So back to the unit circle, I'm going to be using the answer in quadrant 1 with a positive orientation, and that spoke is already labeled positive pi over 4. So the arcsine of radical 2 over 2 comes out to be positive pi over 4. So now I just have to take these 2 points in exact form and find the exact slope of that secant line passing through those 2 points on the arcsin function. You would get an estimate by using these 2 points, but since I'm trying to find an exact value, let me keep these values. So using the exact values, we need to find the slope of the secant line. So y2 minus y1 would be pi over 4 subtract negative pi over 4. And then, of course, to find the slope, you divide by x2 minus x1, which in our case would be radical 2 over 2, subtract a negative radical 2 over 2. And then, of course, subtracting a negative is the same thing as adding. So we have pi over 4 plus pi over 4 in our larger numerator. And in the denominator, you'd have radical 2 over 2 plus radical 2 over 2. To simplify, you could think of this as you have 1 pi over 4 added to another pi over 4. You have a common denominator that makes 2 pi over 4. And in our larger denominator here, you have a common denominator of 2. And you have 1 radical 2 added to another radical 2. So that makes 2 radical 2. 2/4 is the same thing as a half. So my numerator, 2 pi over 4, can be written as pi over 2. And then, of course, 2 divided by 2 is 1. So this simplifies out in my larger denominator, leaving you with just square root of 2 in the denominator. But if you want, I'll write that as radical 2 over 1. And to simplify a complex fraction, you copy the large numerator, change the operator of division to multiplication, and you reciprocate the fraction in the larger denominator, which would be 1 over radical 2. Multiplying across, I get a final answer, an exact answer, for the slope of the secant line connecting the 2 points in question to be pi over 2 radical 2. So we have found the slope of the secant line passing through the 2 points whose x values were given in the original interval. So visually we found the slope of this red line that I drew that were passing through the 2 given points. So hopefully you got a good review of the arcsin function, how to evaluate the arcsin function using the unit circle, and how to find the average or change.